Can you see if people are like watching?
I can't see the
I hope the fact that he's busy means that he's good.
YouTube says it's an excellent connection.
Okay.
Turn off your phone.
Yeah, that's my implant.
Language.
English.
So we're gonna go with, you wanna do this?
Yeah, we'll just start do a quick meeting and then.
You are there.
All right. Very good.
Over there. Steve?
Oh, over here.
Yeah.
Oh, where the camera is. Welcome, everybody. We're going to go ahead and get the meeting started. We're going to do some quick club business and then get on to really the whole point of us gathering today, which is to hear about exoplanets, which I'm super excited to hear about from our guest speaker, Mary Lou West, who flew all the way from New Jersey to see thunder over Louisville.
But mostly to come and see you.
Yes, mostly to see us. That was just a little, frosting on top of the cake. So, how many of you are here for the first time? Great. And Greg, you're not, I know you're not here. What's your name?
Dave.
Dave. Okay, welcome. Are you a new member?
Appreciate that. No.
Okay, but you're great. Well, we're super glad you're here. Anyone else here for the first time? All right. So you all know how this goes, right? So I'm Steve, and we have a couple of just items to talk about. First one is that we have Earth Day here at the Parklands next week, and
Do that again. The disco.
it does it itself.
It does it by itself.
Oh, I
Feel
see.
it last month.
Good job.
Okay.
If you stand really still, then it'll stay off.
So with the Parklands we have a partnership with them to sort of do some shared events. So for Earth Day, what they'd love for us to do is bring out a couple of solar telescopes, which the club owns. If you all have a solar telescope or a filter for your telescope that you would bring out, there's going to be thousands of people here, and we're going to have some opportunities to interact with the public. So
Is that tomorrow?
it is next weekend.
Next week?
Next weekend.
Friday or Saturday?
It is Friday.
Friday.
Yep.
Friday.
It is Good Friday, yes. Thank you for that. So if you're interested, then please let us know that you can help out and come out. And you don't have to bring anything either. You can just kind of be part of the day. And I think it's going to be from 5 to 9. So we don't really have an opportunity for any evening viewing. This is the second time, I believe, that we are trying to do sort of live streaming of our meetings. We have decided that we have 3 people online. Hello, 3 people online. But we have decided that that is an important step for the club to take because we are quite scattered. So if I took a poll about how far folks have traveled to get here, some folks have driven quite a bit. The club goes quite wide. Who are you pointing at, Ronnie? You pointing at Greg?
These are foreigners. They have visas and everything.
They cross state lines to be here.
I'm on my way to El Salvador.
There you go. But we really think it's a helpful idea to keep people engaged by having occasional meetings that are done by YouTube. It also opens up an opportunity downstream, and John Wheatley is a member of Kalamazoo's astronomy club, and he goes to their meetings because they're virtual, so he attends that, and several of the speakers that participate in their meetings are from wherever, and so it's neat that you can get speakers from other places, and we can all sort of interact without being in physical space, but I think we do enjoy sort of being together. We had been doing some observing after meetings, and it's caused some challenges with the Parklands in terms of folks wanting to come in and start to see things in the night sky while our meetings are still going on. So we've kind of decided that we're not going to try to do that again because it's disruptive to the meetings and the public's not getting the viewing that they want. This is usually Pat Peak's setup, gig. So Pat's out, not feeling well. I wonder if he's one of our 3 people on. If he is, we hope you feel better, Pat. We do some quick announcements, and then we'll get to the star of the show. So any announcements from any board officers? Yes, Ronnie.
I just wanted to remind everybody that, we had rescheduled public night, which was last weekend, because of the, rain and all that. So, we have public night scheduled at the observatory for next weekend, next Saturday, starting at 7 o'clock. So, public's gonna be there. We hope, our members show up for some scopes. That would be great. And then, the weekend after that is member night. So, just keep those dates in mind.
Okay, so 2 weekends in a row, opportunities to,
Both of these are Kirby?
Yes.
Okay.
okay, Kirby and Kirby, great. Any other announcements? All right, very good. Tom, would you like to?
He trips over the camera. All right. I'm Tom Hayes, and Mary Lou and I go back 50 years, is it? Is that about right? I was a senior in college in physics major, and I was signed up for the big astronomy class. And the professor that I thought was teaching it had passed away the previous summer. So I went, well,
Like
who's?
2 weeks before the class.
Yeah, and so I said, wonder who's gonna teach physics 406? And so, well, let's go to the class and see who shows up. And Mary Lou shows up, and I said, who is this? She had just gotten her PhD from Columbia in astrophysics, and first real life gig, I guess, and been teaching at Montclair State in New Jersey until she retired. So I was in her first class, and 50 years ago, and we've stayed great friends ever since then. We've gone eclipse hunting twice, 2 different solar eclipses. Last October, we went to Iceland together to look at aurora, and just had a great fun. She is a wonderful person. Mary Lou, it's all
Thank
yours.
you. So it turns out, at least my experience as being a college professor, is every 5 years or so you get a really, really good student. And Tom was my first really, really good student. So I'm very glad to be still his friend. That was great. So the topic tonight is exoplanets and their architecture. So I am Mary West at Montclair State University, retired, emeritus. So my website, my email rather, is westm@montclair.edu. If you want to have any questions, just send them ahead, that's okay. So the big questions we want to talk about tonight are sort of philosophical. What is our place in the universe? Are our assumptions about planetary formation correct? Now that's a real one. Is life abundant in the universe, and is there intelligent life on another world? Or as some of my people in my club say, is there intelligent life on this planet? Well, I don't know about them. Yeah.
We know the answer.
So first, we do have one sample of planets, which are massive bodies going around a star, and that's our solar system. So I want to see what you folks know. So how many planets are in the solar system? Altogether there are?
8.
Great, there are 8 of them. Great. Can you name them in order of orbit size? So let's think about that. So the first one closest to the sun is called Mercury, and then comes Venus, and then comes Earth, and Mars, and good, and Saturn, and very good. A lot of people have problems with Uranus and Neptune. It doesn't really matter, they're twins, so whatever. But now something a little bit more sophisticated, a little more difficult. Can we name them in order of planet mass? So I think it's easiest on this one to start with the big one. What is the name of the big one? Jupiter. And then slightly less massive is Saturn, and then Uranus, and Neptune. Earth. We are the leader of our group of planets. So there's Earth, and then Venus, Mars, and Mercury. Okay, you folks know a lot. This is great. I'm really, really pleased with this group. So, there are 3 types of planets within this group of 8. Can you name any of the 3 groups? What's the group that Jupiter is in?
Yes,
Gas giants, or sometimes they're just called giants, or sometimes they're just called Jovians, because Jove was another name for Jupiter. At any rate, so there's the gas giants. Then what's the group that the Earth is in charge of?
Rocky.
Well, there's a technical word for rocky. Starts with a T.
terrestrial.
Terrestrial, which just means Earth-like. So the first ones are Jupiter-like, and the second ones are Earth-like. And that means we're rocky. What's the third group?
Ice giants.
No,
Dwarf planets.
no, it's the dwarf planets. All right, good job. And who's in charge of that one?
Neil deGrasse Tyson.
Well, probably, yes.
The minor planets.
Neil is a character. Yes, they're called the dwarf planets or the minor planets sometimes, but it's Pluto who's in charge of that one. Pluto is now king of the dwarf planets. That makes some people feel much better about that situation. I don't know. So I thought it's interesting to see some pictures of what these really mean. We know the words, we know the list of planets by these attributes, but these are models to scale of the planets in the solar system. So Jupiter is indeed the biggie, and Saturn is not all that much smaller. It is quite a bit smaller, really. And then we have the twins, Uranus and Neptune, down there. And then the little terrestrials, so Earth and Venus, and then Mars and Mercury. And then just for scale, they put Pluto on this one, too, even though we know Pluto's not one of the major planets anymore. All right. Now, the next one, we're going to take the same set of objects and add to it a model of the sun. So there you go. Is it clear who's the biggest one in this group? Who's in charge? Yes, we know who's in charge. At any rate, so even Jupiter here looks pretty small relative to the sun. But at any rate, I don't know if you could estimate this here, but Jupiter, you could get about 10 Jupiters across the sun's diameter there. So, you know, it's really quite a bit smaller than the sun. I think we missed something. Sorry. Oh, I missed a question on this one. So after we named the planets in order of their mass, then we should answer this question. The sun is what percentage of the total mass? So suppose we had a big basket and we had all these planets in it, and we took the sun and moved it off. So I'd like to do a little experiment here with you. The sun is more than 50% of the mass of the solar system. How many people think it's more than 70% the mass? Put your hand up. Okay. How many think it's more than 80%? Okay, we lost a few. How about 90%? Didn't lose anybody, I don't think. How about 99%? Twins, right? And so it is 99.9% of the mass of the solar system is in.
It's haunted.
It is haunted of the sun. So, to the very first approximation, the only thing here is the sun. And to the second approximation, the only thing here is the sun. And to the third approximation, there's a sun, oh yes, and one planet. And then the rest of us are just crumbs. Right? But we're really lovely crumbs, don't you think? Yes, of course we are. Okay. So there's the models. So now I want to talk about planets in other solar systems, not ours ourselves. And in fact, how could we even find them? There are 3 basic measurements that one can make about a dot in the sky. First, photometry, how bright is the dot in the sky? We can measure the luminosity, and sometimes luminosity changes if those occur. Second is spectroscopy. You slap a grating in front of your camera, and you analyze the star spectrum. This is a very powerful thing to do. And the third one is astrometry. You chart the star's position in space. And stars are all moving. Some are moving this way, and some are moving that way, and some are moving this way, and some are coming toward us, and some are going away from us. But there's movement there, and that's very delicate and difficult to measure. But if we could do that, we could learn something about them also. This is all very difficult. And now we know that they are there even if we cannot see them, which is very subtle and hard to explain to a child. So this takes, any of these three methods takes complex specialized equipment, accurate calibration and operation of it, and requires usually numerous or lengthy observations over a period of time, days, months, years even. So I think one of the things that a lot of people don't realize is that the calibration, the second one there, is very difficult. It's very hard to maintain a calibration over a period of years. Go away. Didn't work.
It'll turn on.
It's haunted. There you go.
There you go. Because if we think about Jupiter, so if we think about looking for a planet in this system, the biggest one, the easiest one to find would be Jupiter. How long does it take Jupiter to go around the sun?
27 years?
Nope, try again.
28.
Nope.
Less. Less.
Less, go less.
12.
12. There you go. And so if you really wanted to do something, I suppose you'd have to do it for 12 years. Oh, for heaven's sake. So that's a commitment, you know, and you got to keep your calibration going for 12 years. Well, to use these methods, these techniques and the methods that have been devised to use the techniques, there's there's 5 main methods. Bottom 2 are hard to use. The main one is transit method. The planet is going around its sun, and it goes in front of the sun as we see it, and that dims the light from the sun, the star, and then it passes on. So you have the light of the star, and it goes dim for a while, and then it comes back up again. All right? Radial velocity approach is that these things are moving. That's the old definition of a planet, right? A planet is something that moves through the stars. The star field is constant and forever, as the ancient people thought, and then the planets move through the star field. So that's why for a while the moon was a planet, because it moved through the star field, which it does do, but definitions do change. And the radial velocity then is if the star system is oriented more or less planar to our line of sight, then we see things coming toward us and things going away from us, and you can measure velocities by means of spectra, and that's very powerful if you can do it. Direct imaging, this is the holy grail. You take a picture and there's a star with a little dot next to it, and the little dot next to it moves. Woohoo! Tough, really tough. This is can you photograph the moth near the porch light from Philadelphia, somewhere far away. Then we have gravitational microlensing, which is something that was predicted and then shown to be true from Einstein's general theory of relativity. It does work, but it's really tricky. But it has been done, and couple hundred planets have been discovered in that way. And then there's astrometry. Can you see things moving in circles, or in fact going that way through the sky with a zigzag line? A few times. So in this animation, I'm going to show you the transit method. You're going to see the little planet up at the top there go around its star, and then we're going to move the camera to when we can see it going across the equator. And then in the lower left-hand corner, there's going to be a graph of the light of the system as it goes along. And you have to remember that the planet is an opaque piece of rock. Okay, here we go. So now we're going to shift our view. Now it's going to go across the equator. Watch the light go down. See it go down? Whoop, goes back up again. This animation is for a very big planet. They don't usually come to be that big, but at any rate, so the light would go down, but in general it goes down only 1% of the brightness of the star. So 1% is not too hard to measure, but 1/10 of that is very difficult. And then you get into what are called millimagnitudes, and that's really tough. Did the light go down? Oh, I'm not sure. Did it come back? Oh, I think it did. Well, toughness. Okay, so the transit method has some advantages and some limitations. The advantages are, if it works, you can measure the radius of the planet. Well, that's pretty cool. You get it as a function of how big the whole orbit is, but then you could usually figure that out. So you could get an actual size of the planet. Is this a little one? Is this a big one? Whatever. You can get very precise measurements of this if it does it multiple times. Usually does. There's a potential with the transit method of getting atmospheric data, because as the planet starts across the star, its atmosphere on the planet hangs off behind it a little bit, and the light of the star comes through the atmosphere and illuminates it. And if you're quick about it, you can see something about the atmosphere. Is it cloudy? Is it only just hazy? Is it clear? Has it got carbon dioxide in it? Has it got water vapor in it? Ooh, neat stuff. All right, but there are limitations. The orbital alignment with the Earth is very much required. So the planet has to go right across the star, like across the equator. It can also go across, more toward the polar region a little bit, or in a slant, something of that sort. But in general, thank you. In general, the planet's orbit has to be within 1 degree of the line of sight from us to the star in the first place. And so you think, well, there's a couple hundred degrees in a circle, and we only got one of those. So whatever you get, you're going to miss 200 times or 300 times whatever is there. So that will have to be figured in if you're going to do statistics. This, of course, is less efficient for small planets. It's very hard to tell if a teeny thing goes across the front of the star compared to a big fat thing, all right? False positives are very prevalent, especially from eclipsing binary stars. So the number of stars that we see in the sky most of them, or 3/4 of them, are in double star systems. So you have 2 stars going round about their common center of mass. Now our star is not. Ours is a singleton. And so that is somewhat unusual, all right? But if you have a system where you have a big star and a big bright star and a little faint star going around each other, sometimes the little faint star will be dense enough that it takes away some of the brightness of the big star as it goes across it. You can say, well, that looks kind of like a planet. And that's very difficult then to disentangle. And most of the transits we see come out to be eclipsing binary stars. I think it's interesting to think how to decipher that. And it depends on knowing something about stars. And in particular, the size of a star, real physical size, often tells you something about the color, the temperature, or the color of the star. So what color is our sun?
Yellow.
Yellow. Lovely yellow thing in the sky. But the little stars, the small stars, are not yellow. They're mainly red, often fairly deep red. So if you had, for instance, a nice yellow star with a little red star going around it, if they're really, really little, they're called brown dwarfs, so they're just dark brown. At any rate, if you have a star like the sun and a little red star, the main color, the color you would see if you photograph the whole system is yellow with a tinge of orange in it maybe, right? Then you take it and you let it go to the eclipse part where the little star is now in front of the big star. And now you've taken away a chunk of bright yellow and replaced it by a wizzly little bit of dark red. So mainly the star becomes less yellow. And then it passes on, it gets more yellow again. So if you had two color filters and you could watch the whole transit, say in yellow, and then watch it again in green or any other color, then you could see that the color changed during the eclipse. If you have a black opaque piece of rock, it makes the light go down, but the color stays the same. So it's this color change that can be used to decipher this. But that's tricky. But there is a way. And to do the transit method and get some real information, it requires periodic observation over long times. So you watch a transit, and then 12 years later you see another one. Or for something like the Earth, you see a transit, and then a year later you see another one, and then a year after that you see another one. So it does take quite a bit of time. And I'm going to come back to the time in a few minutes. The main source of information about these transits are spacecraft, and Kepler was the first spacecraft that really did this exceedingly well. So there's the spacecraft on the left. It's kind of like the school bus sort of thing, size. And on the right, you see the portion of the sky that it looked at. It stared for several years, 7 years, at that portion of the sky. So it's in Cygnus Lyra sort of region. Each of those little boxes there, the 3, the 5, the 5, the 5, and another 3, each of those is a different CCD camera. So each camera looked at only a portion of that and was very steady at looking at its own portion. And it took pictures every few minutes for years. And then it lost some steering capability and it was very difficult to hold on any object. And then it became not Kepler K, but K2, and did some stars for 2 years, and then the whole thing died. But we did get some more information after that. I thought that was marvelous, if the NASA people could make it work. So here's 2 panels, which are plots of the brightness of a particular star. The star is called HAT P7, and time goes across the bottom in days, and it goes up to 2.6 days for some reason. At any rate, this is a transit, and I call your attention to the bottom of these figures, in which you have a straight line going along, and it goes down and across and up and back to the straight line again. This is real data of a transit of a planet going around HAT P7. HAT, does anybody know what HAT means? HAT is for the Hungarian Astronomical Group. I don't know what the Hungarians were up to, but they got this one, and it was very nice. This is Kepler's version of it on the bottom. On the top, we have measurements from a ground-based telescope. All right? Can you see the transit there? Yeah. What else do you notice? It's a lot of noisy, fuzzy stuff there. And why is that?
Atmosphere.
Because we're looking through the atmosphere. And our atmosphere is not steady and laminar, but it moves around a lot, and sometimes makes tornadoes even, and things like that. So this was clear air, and telescopes on the ground looking through clear air, and yet it wobbles a lot, and the stars twinkle. And that's what you see in trying to collect data.
How big of a dip is that?
This was, I think, about almost 1% of the light. This was an easy one. My group, we measured HAT P3 one night, and it was about 1% and looked really messy. But at any rate, it's really good to be in space, don't you think? Think it's more expensive? Oh, yes. Oh, yes. So here's my group. I'm that one there, the little one. This is my club in Cranford, New Jersey, sort of upper middle of New Jersey. we have a 24-inch telescope, this job here, which is really, really wonderful. And so this is the group that started out doing transit measurements. This person here next to me is Dennis Conti. He's the one in AAVSO who runs their exoplanet group and runs courses, the choice courses, and how to do this technique. So people in my group took the course and we learned how to do it. And then Dennis came and really taught us how to do it. He lives in Maryland, so he drove up to New Jersey for a couple of days and taught us how to really do it. So this is one of our sets of data. This is HAT-P3, which we didn't discover. We already knew that it had an exoplanet in it. See, it works. So anyway, there's many lines of data just offset arbitrarily, and this is a period of like 6 or 8 hours. So here's the light of the star coming along this way. Then it begins to fade. Then it's that level for a while. Then it increases again, and then goes back to its normal variety. So you fit the software, the AAVSO software that they give you, fits a model to that. So the model goes across, down, across, up. And then this is the important part here. This one here, the third line down, is the residuals, the difference between the model, the straight line, and where your measurements were. And it's important that that looks pretty random, and indeed it did. You don't want to see any long-term trends. Oh, stop that, sorry. Where'd it go? Come back, come back. Where'd it go? There it is, sorry. And then the next 5 lines down are other stars in the same field of view, and those are all pretty much straight across, which is what you want. We were worried about the green one, 1, 2, 3, 4 down, as might be a variable star. Sometimes you see really nice variable stars, and they go up and down and up and down, nice sinusoidal variation. And that one then you throw away. It's not a good comparison star. So now let's see if I can do this right. Okay. The next method is the wobble method, or the velocity, or the Doppler shift method. So here we're going to have another animation. We have the star in the middle, and the planet is now at the bottom, and we're going to watch it go around. And then what happens is that the star and the planet are going around their common center of mass, which usually is within the star itself. It's not very far out from the star center. And as the planet swings a big distance around, the star swings a little distance around that. Well, from Earth, which is far away from everything, you never see the planet. You hardly ever see the planet, but you can see the star, and you can see the star doing a little swing dance in there. And that's what you're going to look for. And that involves a velocity, not just a position. And with velocities, we know that if something is receding from us, it's redshifted. And if it's approaching us, it's blue shifted. The way I remember that is that receding and red both begin with RE. And therefore, they go together. So in the bottom, you can see the color of the light. So now the star is going to come toward us, so it's blue shifted. And then the star is going to go away from us, and it is red shifted. And you don't get any colors from the planet itself. Okay. So this radial velocity method, by which you measure the color of the spectral lines, has some advantages and some limitations. It can measure not only the orbit, but the orbit eccentricity, because the velocity within an elliptical orbit changes with time. It gives you an estimate of the minimum mass of the planet, but if you don't know the tilt, you can't get the real mass, just the minimum value. If you have that method, which gives you some mass, and you also have the transit method, which then you would do immediately if you knew this was a real planet, get somebody else maybe do a better telescope to do that one, then you could get the density. And that's very important. is the planet as dense as rock, like us, or is it more the density of gas, like Jupiter? Haha. And then we can detect other things. It's, of course, easier for larger planets and harder for some of the others. It's difficult to do. You need a spectroscope that is very sensitive, has a great dispersion, and sometimes spectroscopes are very sensitive to temperature, so you have to have the spectroscope in a room that's very constant in temperature and doesn't change at all over a period of years. Oh dear, oh dear. And another problem at the bottom, there's false positives with this due to stellar activity. So if its star is shooting off coronal mass ejections, then the star is coming toward you. Thank you. So it suddenly looks like the star is coming toward you because there's this blob of hot gas coming toward you, rather than it may actually be going away. So you get discordant points in trying to get a sine curve out of that. Direct imaging method, I think, is really exceedingly amazing that anybody has ever taken a real picture of some planets, but there have been people that have done that. There are sometimes just lucky things that confirm a candidate for this. The type of material, so at the bottom we have the limitations, and particularly you need for this some sort of object to block the light of the star itself, because planets are so faint. So the one that people generally think of is, stop it, sorry. Let me go back further. There it is. This one here, which is a coronagraph, and people, it's like having an eclipse with the moon coming in. You just see the edge of the star. Or you have a piece of cardboard big enough that it covers the whole star, and then you take longer exposures, and then you hope to see a little planet over here, or maybe a little dot over there. The one that is really high in the sky sort of thing is a sunshade, or a star shade. So that's this upper one, that's this thing which is like a daisy or sunflower all packed up together, and then it expands when it gets out in space. And here's a spacecraft looking at it. And that sort of peculiar shape is very good at blocking not only the light of the star, but the little wisps that come out of it. And yet it has cracks between those that allows you to see between those. And if it's turning, it suddenly will show you one of the planets. Strange and wonderful. Then another method is the gravitational microlensing method. I think this is really cool, and I'm amazed it actually works. So the advantage of this one, it can reveal planets in very distant star systems. So most of these others require the star to be, with the planet to be near to us, or bright, or somehow accessible. This can do it for things that are thousands of light years away. All right. It's suitable for observing large number of stars in the center of the galactic bulge. So what this requires is two stars that line up perfectly on our line of sight. And what's happening is there's some star way over there hardly moving, and then one of the other stars comes between us, exactly between us. And then the lens, which is the in-between star, brightens up the thing behind it, so suddenly it's bright for about a month, and then it goes away. But that means this is a one-time observation only. It never is repeated. So you learn there is a star with a planet right there. Stop that. Go away. Thank you. So this yields a limited amount of information and requires a tremendously precise alignment of the planet, the star, and the Earth. But it's really, really cool when it does it. And we have so many stars, if we look toward the center of the Milky Way, thousands and thousands of stars there. And of course the Milky Way is spinning, and so these stars are all moving. And there's just so many of them that there's a possibility that, like, 10 times a year, something's going to pass in front of something else. And we've actually seen this happen. So here's an animation of this one. A mass like a star creates a dent in space-time. Now we're going to have the star with a planet. That's this little trap, sorry. I'm sorry. Yeah. Try again. There it is. So the star with the planet is going to cross in the middle of our screen from left to right. And it's going to bend these shards of light down toward the Earth, which is at the bottom. You see a little bending of lights there? And then we have, on the right-hand side, the curve, which is a big lump, takes about a month, and it got a little chick on it when the planet was in there. And we've seen hundreds and hundreds of these things. Thank you. So astronomy, astrometric measurements, requires no special alignment at all. You're just going to watch for some little light in the sky to make a circle or an ellipse. It's the potential to detect very wide orbit planets without waiting 12 years or more. Sometimes you have to wait quite a lot anyway. Can be used to measure the mass of the planet, which is useful. Limitations, it requires precise measurements, very, very fine resolution in your telescope. And it's most effective for nearby stars and big planets. So here's a measurement, shows you how this measurement is made. So we have again the center of the very center. And we have 3 stars on the outside here, which are reference stars. The star and the planet are the thing in the middle, and I don't know if you can see that it's going around. Can you see it going around? It's really tiny. And that's the problem. To measure the teeny tiny thing. Because it really is going around. But stars are very far from us, so this is a difficult thing, but occasionally it can be done. So here's the exoplanet discoveries by method. The first line there is the transit method. That's about 4,000 of them are discovered. Radial velocity approach, the Doppler, that's another 1,000 of them. Then we have the microlensing and looking toward the center of the galaxy. We've got 200 of them that we've seen. Direct image, 82. I find that hard to believe, but that's what I read from the NASA site. And astrometry, 3 of them. Okay, so it's nearly 6,000 planets that we know at the moment. I think that's amazing. When I was little, there were 0. And then in 1995, things started happening. And, 30 years ago, and in the next 30 years, we've discovered 6,000 of these little guys. This is fantastic. So the way you can calculate mass and other variables from these things involve Kepler's third law. So the period squared is the axis length cubed times some constants. And if you know any of period, axis size, or mass, which you never know, you could figure out the other one, the third variable. And getting 2 out of 3 is fun. So the search began. So in 1938, which I don't remember, D. Beloritsky proposed using transit photometry as an idea. And everybody said, well, sure, someday. Then in 1952, Otto Struve suggested using spectroscopy to do this. And nobody had a clue how to really do that either. Then in 1992, Wolfson and Frail discovered the first exoplanet. But it was orbiting a pulsar. The pulsar was PSR B 1257 plus 12, or whatever, right? So that was not considered very useful. Does anybody know why it was not really very useful? What's a pulsar? Does anybody know? It's a remnant of a supernova, which should extinguish all its planets, leaving you nothing to look at. And yet, here we had, in fact, 3 of them going around this one little pulsar. Nobody understands that yet, how that could happen, how they could survive the explosion. We don't know. Then in 1995, that's when things really got going, Mayor and Queloz discovered the first exoplanet orbiting a main sequence star. Yay! All right. So here's a little bit about it. The star's name is 51 Pegasi. Guess what constellation it's in? Very good. All right. And so it was discovered using the radial velocity method. Here we have some graphics of what we think they look like. So the planet is just a tad bigger than Jupiter. Its star is a tad bigger than our sun. So it's not much different, really. It has a really, really close orbit, though. It goes around the star in 4.2 days. Whoopity, 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 whoop. How long does it take Jupiter to go around our star? 12 years. That's a lot of days. This thing goes around in 4 days. Whoopity, whoopity, whoop. All right. This got these 2 guys the Nobel Prize in 2019. All right. So I wanted to tell you a little story here which has a moral to it. Really interesting at the time. So in 1995, they started to observe this star. They looked at it for a month or so and said, let's really do the math in our data. They did the math. And they said, 4.2 days, good Lord. And they announced it. Meanwhile, Butler and Marcy had been observing this star among a whole passel of other stars for the last 5 years. And they had not done the math yet. They didn't do the math because they didn't figure it was useful. It would take 12 years for Jupiter to go round, so they expected to do everything for 12 years and then reduce all their data all at once. They were scooped. They were scooped big time. So as soon as these 2 released this discovery, Butler and Marcy reduced their data, and sure enough, the star was been going around every 4.2 years, 2 days for 5 years, and they hadn't noticed yet. So, if you have data, reduce it as soon as you can. Don't wait. They felt terrible. Well, one of the problems with exoplanets is confirmed versus candidate. So there are on the order of 6,000 confirmed planets now. You can point in the sky and say, that star over there, that has a planet, and so does that one, and this one has 2 of them. And there's 7,000 that were detected by the satellites, but not confirmed yet. And you have to be confirmed by 2 more telescopes, different telescopes, and almost all that means it has to be somebody on the ground to do it. And that they need people on the ground to do the confirmations, right? There are 4,000 of them with multiple planets. So mostly this is a system where there's 2 planets going around 1 star. All right. There are numerous false positives. So at least half of the possible planets turn out not to be planets at all, rather these little stars. There's a large backlog of candidates awaiting confirmation. So first it was the Kepler group, now it's the TESS group, which is looking for people on the ground in astronomy clubs. Here you are, all right, who can master the technique and look for confirmation of particular planets. So they will tell you, there's a long-running list. In the constellation of Blah, there are 17 possible ones. Pick one of them tonight. Or this one is eclipsing every 27 days. So the next comes up at, tomorrow night. And we want somebody to do the color test on it. Nobody's done the color test on it. Would somebody please volunteer to do the color test? So I was a part of a group, as you saw in that thing of a group, we were the Celt group, so I have Celt on the back of my t-shirt, run out of Lehigh University, and so New Jersey's not very clear, we had a lot of cloudy weather, but if a clear night was coming up, we'd say, okay, let's go see what we can find, and we'd look at the list and pick some star that possibly was gonna have a transit that night, and we would do that measurement like we did. And in all the ones we did, they were not planets. It was a bummer, but that's what they need. So we were called the follow-up network, or the fun people. Yes, I am part of the follow-up network. Yes, and we did have a lot of fun, but it eventually got discouraging. But then eventually you get your name on a real published paper. So after they get 100 people, they publish a paper and your name is on it. And so 5 of us in the group, that picture I showed you, have a published paper. It's really cool. There's conventions about how to name new stars and planets. So the first part of the name is either the telescope or some other way, or the spacecraft. So most of the ones were Kepler something something, or so K something something, or Hat something something. The Hungarian group had a list. Very few are Henry Draper, but some are Henry Draper numbers, the old style. And then you get a number, the order in which the star was cataloged, or generally the number in which it was done. And then there's lowercase numbers for the planets. So if there's a capital A or B, then it's a multiple star system, and those are star designators. But if it's little b or c, then it's a planet going around whatever you just named. So the last one, in multiple star systems, like Proxima Centauri, the uppercase letter designates which star it is, and the lowercase letter which planets are there. So some are very complicated. This is one of the spectroscopes. This one on the ground. So this is, sorry. This one here has a spectroscope in it. It's sealed in the container. It's bolted to the ground. It's in a room where they lock the door, turn the lights out, keep the temperature the same, and then do the pipe the light into there. So you try to particularly minimize problems with temperature. The Gaia satellite, which in fact was disabled just a week or so ago because it got really low on fuel, was wonderful. This is one did astrometry, but also was wonderful for all the other methods. This satellite just took pictures of the whole sky, did it with tremendous accuracy, and made a 3D map of all of space, and giving every star right ascension, declination, and distance from us. So it was, its data goes into a lot of things. The real new one is TESS, Transiting Exoplanet Survey Satellite, launched in 2018, still going strong. Has a highly elliptical geocentric orbit, so it's going around the Earth, has a very wide field of view, takes pictures on, I think, a 2 or 4 minute cadence, looks for the transit method. So they have a big pipeline in a computer of taking each of these images and comparing it with the last 5, looking for anything that goes dim in light. It has discovered approximately 500 confirmed planets now and over 7,000 candidates, all awaiting confirmation. So what we've learned so far, exoplanets are mostly found by satellites, so Kepler and TESS, looking for the transit brightness dips. This is the real money way to do it. We now know about 6,000 planets for sure, and half of the stars looked at have a planet. Half of them. Some of them have 2 planets. That means that there are roughly 1 planet per star on average. Is that cool? So when you look up in the sky, you look at the Pleiades, for instance, there's probably an equal number of planets there as there are stars in that group. Just think about that when you look at that the next time. We test the candidates from the ground singly, one by one, and there is one system in which there are 8 planets. Cool! What a good number, don't you think? Yeah. Whoa. And there are some planets in binary star systems, and they are almost always orbiting one of the stars, but not both of them. So there's some cases which I think are not going to last long because the planets are orbiting one of the stars, and the 2 stars are really pretty close together already, and they're going to nip off one of the planets and send it slinging out into space. And here's an unfortunate thing. Most of the stars in the sky are flaring red M main sequence stars. So they're cool stars on the main sequence, the M stars, not giants, just small M stars. And they have a tremendously rough flaring and X-ray flux coming from them. So if there were life there, it wouldn't last long, just get blasted away. And then there are some systems which have very weird orbits. So these are really exciting to think about, but mind-boggling. So our solar system is very flat. Everything goes around the sun in a flat plane. And there are some systems where some of the planets go around a flat plane, others go very tilted. What the heck happened there? I don't know. And there's some of them where a couple planets go backwards to everybody else. What happened there? You have no idea yet. There's many models, none of which we know for sure. And then there's the ones in which the Jupiters are right next to the star. They're called hot Jupiters. They're zinging around in 4 or 5 days. What's happening with them? I don't know. So some of these odd ones are really interesting to think about. Here's another interesting thing to think about. The number of stars, or the number of planets rather, going around other stars. There's a bunch of big ones, and then there's a few more that are the Uranus-Neptune size, and then there's even more at the terrestrial size. So it's as you might think, there's lots of little pieces and only a few big pieces out there. But this is interesting. This is the end of the distribution toward where the Earth is. So there's the Earth there, and the Earth is at this level here, that one, that size. And then here we have Neptune, and Neptune's that size, and Uranus is here. Stop that. So this distribution is called the super-Earth to the sub-Neptunes. All right, down at the bottom. And look at this. There's something wrong with this distribution. There's a hole in it. And this is called the radius valley. So this is a plot of radius versus number of stars, number of planets, and there's this valley here. So what people are thinking now is that this distribution used to go straight across there. And then something in here takes the planets once they're formed and gets them a bigger radius or gets them a smaller radius and gets them out of that particular gap there. So how does a planet get a bigger radius? Well, it puffs up its air and makes it all smoky or cloudy. Because what you see as a radius includes where the clouds are. That's what we see, right? Or on the other end, the planet loses its atmosphere and maybe some of its soil is blasted away as well. We don't know, but I think this radius valley is very intriguing. We shall see. And here's some interesting ones, just to give you an idea of the distribution of stuff. Here's Jupiter here, and there's the Earth there. And here's some of them that are bigger and all fairly similar. And then down here, here's the Earth, and there's the bigger one and then littler ones than the Earth. So all sorts of interesting things. And there are 6,000 of these guys that we can play with. So if anybody, the rest of you are data junkies, you go to NASA exoplanets, and you can play around. One of the ones that's an interesting special case is Proxima Centauri. This is the nearest star system to us, a little over 4 light years from us. And a few years ago, so 2016, it was discovered that there's a planet in that system. Well, 4 years, if we could get to the speed of light or even near that, suppose a tenth of the speed of light takes us 40 years to get there, 40 years to get back. In 80 years, we would know something about a real planet. Wouldn't that be cool? Well, we're not going to do it, but we may do something like that. So there's a proposal at this point to take a whole bunch of iPhones, take 1,000 iPhones, put little rockets on them, send them to Alpha Centauri. You can get them up to 10% of the speed of light with not much trouble. They're very low mass. As they whip by the thing, have them take pictures and send the pictures back. Cool. Some of you younger folks may get to see that actually happen. So cool. So here's another oddity. So this is a transit. So brightness goes across, is the y-axis, and then time goes across the x-axis here. This was taken by my friend Mario Mata in the Boston area. He has a 32-inch telescope in his home observatory, which he made by himself. Oh, he's got a lot of power there. So Mario measured it, and this particular star has a very strange transit. So remember, they're supposed to be U-shaped, watch, oh, come back. Where are you? Where'd you go? Okay, but it has this lump in the middle, and that means there's really two objects going across and clearness between them of some sort. He didn't know if it was real, but the picture on the right was taken the same night by Dennis Conte in Maryland, who has only an 11-inch telescope. So he can't take quick exposures like Mario can. He has to take longer exposures, so the points are farther apart, right? But it is the same pattern. Can everybody see that? And it goes gadung gadunga, and this goes gadung gadunga. Same pattern, so it must be real. And the star is interesting in this case. This is a white dwarf star, it's a little bitty star at the end of its life. And it's calling us. Oh my goodness. So this star has something that has two bodies going across at almost the same time. And it turns out to be a polluted white dwarf at that. So that tells us that this is an asteroid or a minor planet, maybe Pluto-like, I don't know, going across in front of this star, which is in the process of falling apart. It is disintegrating.
This data is reproducible in next orbit?
And the next orbit, it was different. There were 3 pieces.
Oh, really?
And the next orbit after that, there were no pieces. But then the next orbit after that, there were 2 pieces again. So, but they were different in size. And then it eventually cleared up and there was nothing transiting ever again. But the interesting thing, the other interesting thing about a white dwarf is it has a very bland spectrum. Just little hydrogen, mostly helium. But sometimes they are polluted. And polluted means that the spectrum suddenly gets iron and nickel in it. And then it disappears. So we think that these white dwarfs, many of them have disintegrating bits around them. It has very fierce gravity, so that once the atoms come down into the planet's atmosphere, they may last a month in the upper atmosphere where we can see them, and then they sink out of sight deep into the white dwarf. Poor baby. So the summary here, what I want to tell you is exoplanets do exist. I think that's amazing itself. And there are lots and lots of them, thousands, and it's an exciting time to be alive, don't you think? Many of them are very strange, and Tess will need lots of fun people who should volunteer. So I thank you for your attention, and I thank you for paying your taxes, especially at this time of year, because some of your tax money went to the James Webb Space Telescope and the Hubble Space Telescope, and Tess and Kepler. So, and I also want to thank Chris Morrow, who's also in my club, helped me find all these animations, which were great fun. Thank you very much for your attention. Can we turn any lights on other than this one?
The little,
I can
the little slidey thing on the right.
slider on the right.
No.
Yeah.
Left side, right panel.
There you go.
There you are.
Now it
Any
won't come
questions? What you
I
got?
have so many questions, but I'll start with are we looking at a single star at a time?
Yes.
Is that how the process goes? It doesn't look at a field of stars and do them all at
Well,
the same time?
yes, the big satellites, Kepler and TESS, look at a big piece of the sky, million of stars at a time, and they just take that picture, take that picture, take that picture, take that picture, and then the computer says, oh, this one here just went down, that one up there just went down.
Okay.
So it's done with the computer once you take all the pictures. But from the ground, to make confirmation, is one star at a time.
So that's how the science advances. It's sort of like all the candidates, and then it's like, okay, here's a list of candidates, and the observatories are like, we're gonna work on this, we're gonna work on that, and that's how it
Right.
usually unfolds.
Right, and so anytime you make one of these observations to test a candidate, it's a commitment for only one night. So we would spend 6 or 8 hours at the telescopes. We'd be there 10 o'clock at night when it gets really dark. Then we would start one of these data takings, and it goes down for 4 hours and goes back up. And then we would have food and go home. But there are just now way more candidates than we can deal with, and they're really looking for people who could help out from the ground and who can show that they are careful enough that they could detect this sort of thing. So I encourage somebody to look into it and see if they could do it. We had fun for a while, and then some of the people in our group moved away, and then it got rainy for 7 years, and you know, so we're not doing it anymore.
So, I'm sorry, with the confirmation piece, though, you have a sense of when it's
Yes,
most likely?
yes, the list that you can see at the Kepler site or at the test site tells you for the next month, these particular stars are predicted to have an eclipse, you know, a transit on, you know, April 17th, starting at 4 in the morning. Well, that's not good for us. There's another one on the next day starting at 10 at night. Oh, we'll go for that one in New Jersey. But the earlier one, the Europeans would pick that up, you know. So it's, you know, what good time for, when it's dark in your vicinity. And half the time, you know, in New Jersey, half the time we get all set up and we'd see the star and it would go out, and we'd go, oh, look, it's all cloudy. Let's go home, let's go to the diner, okay. But anyway, you know, it's really exciting when it happens, and disappointing when it doesn't, so that's what happens. We got another question.
So the planet orbiting the pulsar, has there been any recent observations of that, or was it a false?
I don't know, no, it is not false.
It wasn't false?
The planets, there were 3 planets orbiting the pulsar, and they were followed for some years, and they're still going around then. I don't know of anything
New.
recent. But that's a real conundrum.
Could they
3
have been-
planets somehow survived a supernova
Could they have
explosion.
been captured?
Maybe they were captured later.
That's interesting.
I don't know, you should look into that.
Do we have to worry about being captured?
I don't know. How did they happen to capture them? They went through a string of planets just sitting out there? I don't know.
Well, you know, it's, I think it was James Webb, they found a bunch of rogue planets in Orion.
Yes, there are rogue planets that have escaped from their star and just sort of,
But the
Wandering
number that
willy-nilly.
they found in the network just surprised everybody. But they just found hundreds of them. Just rogue planets running around inside the Orion Nebula.
the Orion Nebula is a very fabulous
Yeah.
place. I don't know. So we shall see, but it's an exciting thing and it's ongoing. I'm part of a group at Princeton University. We have an exoplanet discussion group. I don't say much, I listen a lot. And we discuss every week, we discuss what's the latest in exoplanets. And there's often these weird ones that come up and nobody seems to know, not even Josh Wynn, so. But they're intriguing, and a lot of the discussion I must say, is about sensors and how you make your sensor more stable to temperature. And that sort of thing is really tough to do, but important on some of these things. So,
You showed us a graph that had a gap in it and said this was an anomaly. Could you say more about that?
okay, this is the white dwarf with the disintegrating asteroid, probably.
Oh, okay. I thought it was sizes of planets, and then there was.
Oh, yes, the radius valley, that's another good one.
Yeah.
So there's this sort of distribution, and it went like a bell curve up and down, and then it had this gap in it, it went down, and that's the, this is radius and number, so it was the radius valley. And nobody knows what that could be due to. It's only within the last 2 years that we've actually determined that there is a radius valley, that the statistics are good enough now that that is what's happening. So that's a real current piece of inquiry. What could possibly cause a radius valley? Because the assumption would be this is a really nice bell curve otherwise, just cute as can be. And so you could assume it was that way, and then something took these out. Well, where did they go to? They either went this way or that way, right or left, right? And so, since what we see is a planet, which may be rocky or maybe gaseous, I mean, or maybe just ice, so it's between the size of Neptune and the Earth. And that's rocky and this is icy. So in between there must be a fair amount of atmosphere. And atmospheres of the gas planets in our solar system are all very, very cloudy, like the cloud bands on Jupiter and that sort of thing. So that's the size we see of Jupiter. How much of that is atmosphere? Is there any rocky bit at the middle? Well, Jupiter probably is all atmospheres, no rocky bit at the middle. So to make a gap here, what you do is you take some of it and you take the atmosphere off the top of it, leaving you a little thing so that it moves over here on the distribution. Because that's what you see, right?
Well, we've seen with Mars that if they lose their the planet's magnetism, the sun tends to wipe away the atmosphere of a rocky planet.
Right.
Now on Jupiter, that'd be a whole thing different.
Right. So certainly there are ways for a rocky planet to lose its atmosphere. So with both Mars and the Earth, the atmosphere only goes up like 1%. No big deal. Here you have to really lose 10% to make it move out of the gap. So that's a fair amount.
Mm-hmm.
Another way to do it is they say, well, maybe the distribution was the way of a bell curve at the start, and then the planets were still hot from the formation, and they cooled off and shrunk, and then the atmosphere blew away.
We don't have that gap in our solar system between the largest rocky planet, the smallest gaseous planet.
Yes, we do. There is nothing between Earth and Neptune
okay.
in our system. It's a total gap.
Mm.
But then again, we have 8 points, which is hardly a distribution.
Could any of that be
Small
used
sample
as
size.
observational techniques? Used to have
I don't think so, but I'm not sure. Maybe it is all. No, it can't be all
that. No,
observation.
not all, but it could be.
Problems.
A little bit.
It's bigger than a little bit. It's now, this year, decided there is a radius valley, and we should work on trying to understand why. 5 years ago, there was a hint of a valley,
Yes.
not for sure. Now we're sure there is a valley. Your turn. So you go to a bunch of graduate students who say, your turn, figure it out, you know. One of the wonderful things about astronomy, I think, is there's so many things, there's so many stars, certainly, and now planets and stuff, that there's lots of things that are conundrums and they're fun to think about, right? And they may be solved or maybe not. But you could do it. You could take part in one of them or other. There are a lot of citizen scientist projects, and this looking for exoplanet confirmation is one of the citizen science projects that NASA runs. But I have another one, and so I would like to pass out some cards here. I think I have enough for everybody. So this is for the front group. This is for 3 people.
Is it bad if we get the ace of spades?
Yes, it's really terribly bad. That one. So I will hold on one and then give it to somebody. He's your friend.
Oh, there we go.
An extra.
Great, let's pass the extra back.
I don't know, just.
You have enough?
Yeah.
They didn't get one.
So this is, here we have some more.
Where's Rule? So I just take a couple minutes and tell you about this one. This is my baby. So, HAMSci is a group of ham radio operators doing real science. Are any of you ham radio operators? All righty, good job. So am I, KC2NMC. Anyway, so I am one of the scientists. We have a handful of scientists who run this project, and we have 1,000 ham radio operators in our group. The idea is that the ham radio operators are just going to talk to each other, and the big networks tally up how many conversations there are between every state and every other state. And we use that to decipher information about the ionosphere. So this is a model. We live on the white part down here, the Earth. The blue part is air we can breathe. The orange part is the ionosphere, which we can't breathe. In the lower left corner is some radio operator, and he's broadcasting radio signals in every direction. The signals that go straight up or at some fairly straight up angle just escape right through the atmosphere. They go right through it. But if he sends one that happens to go at the right shallow angle, it hits the bottom of the ionosphere, is refracted, and comes back down. So this person in this corner can talk to this person over here. They can talk back and forth and have a conversation. He can talk to people beyond that, but nowhere in between, and the in-between is called the skip distance, and that's what I studied. So I want more people to talk to each other. And I will just keep the statistics going. So the statistics are pretty amazing. I think there are almost 1 million ham radio operators in the United States, 700,000 and something. There are 3 million around the world. We have on the order of 30 million contacts a day. So I'm doing and I have young people who do the computing for me, at any rate. So if you know anybody who's a ham radio operator, give this card to them. Or if you have a chance, just look up hamsci.org and see what projects we're doing. So I've got the group the last 2 years to do eclipses. So we did a little eclipses of 17, but not much. Did one of the 23 and the 24 eclipse. And I'm still analyzing my part of the data for that. This year, we're doing meteors. So, did you know? A meteor comes going, burns up in the atmosphere, high in the atmosphere. It leaves a little trail of metallic ions. That's really, really reflective to a radio wave. So you're talking to somebody over here in the next only 1,000 kilometers away, and suddenly a meteor comes in there. Now you can talk to the Philippines. Oh my God, for a millisecond. And then, strikes me as not really useful. But we have computer software which then can be set, please detect meteor scatter. Okay, and it does that, and you get how many meteors you saw that night, and it's best at a very peculiar frequency so it doesn't mess up general communications. And just this last year, not only 6 meters but 10 meters has now been allowed to use this software. So we're going to do 10-meter meteor scatter next week, and then for the Perseids in August, and then for the Geminids in December.
So is that just constantly broadcasting or what?
Yes. You're calling CQ, hoping somebody else hears you. You're going to try to divide people into listeners and broadcasters, and at the moment, everybody wants to be a listener, nobody wants to broadcast. Well, that's dumb. That doesn't going to help at all. You know, half people sending and half people listening is better way to go about it. And we're gonna try to get, so we're gearing up for next week and going to the Lyris and trying to get the number of meteors over time and see if our peak matches with amateur astronomers' view of counting little wisps in the sky. So if you want to count, meteors in the sky, please do that part for each of the meteor showers coming up. Thank you very much for your, I don't know. Do any of you count meteors?
We have, well, we still have it. We have a all-sky camera that we got from, the American Meteor Society. It's got 7 cameras,
Great.
and, but it's down right now, but I'm gonna hopefully get it back up.
Can you get it up sooner rather than
Yeah.
later? Yeah, or somebody go out in a lawn chair, just count the number of meteors.
But that's all it does, is it takes video of the meteors. It's in
Right, well,
infrared.
you could do that in a lawn chair, right? That's fun to do. Anyway, thank you for your time, I hope you have a good time. Here's an extra one from the video.
I'm getting an ad on Facebook
Yeah.
about, we have a course and you take it, we guarantee you'll, get your technician's license or something to be a ham. Apparently, because the no longer